Hi everyone, this is Dr. Eric Soehnlen and welcome to Chapter 1 of our Chemistry in Our World class. Our textbook is going to be General Organic and Biological Chemistry by Frost and Deal. So our first chapter is called Chemistry Basics, Matter and Measurement. So we're going to start out by defining what is matter. We're going to talk about how we classify matter, which is the material that makes up the world around us. And in order to do that, then we're going to have to discuss what makes up matter. So we're going to talk about the chemical elements, how they can come together to form compounds, and how we organize them on the periodic table. Then we're going to talk about the different mathematical units that we use and how we do math in the sciences, including chemistry. We're going to go into a further discussion on matter, and then we're going to talk about how we measure matter, and we can talk about how we measure changes in matter. So we'll talk about chemical equations and how we balance chemical formula and things along those lines. So this table represents one of the simplest ways that we can break down matter or classify matter. So matter is the stuff that makes up the entire world around us. It can be separated first into pure substances versus mixtures. Mixtures are things that we can purify into simpler things like pure substances. So pure substances can be further broken down into elements, things that are made up of identical atoms, or compounds, things that are made up of different elements combined together into a single compound. Both of those things are pure substances. Now, if we start to mix elements or compounds together, we can get mixtures. So we can get homogeneous mixtures, which would be an example of two different elements mixed together to make a metal alloy like brass. This is technically a mixture because it's two metals dissolved in one another. So if we think about other mixtures that we're used to seeing are things like salt water. So that would be an example of a mixture. Now we can have homogeneous mixtures, means it's the same throughout. So salt water, brass, those things are the same throughout the entire sample. If you look on the right side here where it says heterogeneous mixture, they've got pennies dropped in a glass of water. So that's an example of a heterogeneous mixture. It's not the same throughout. The copper in those pennies are not spread evenly throughout the water in that glass. So that's what we would call a heterogeneous mixture. Another example of heterogeneous mixtures would be like a marble countertop. Like if you look at a marble countertop, you can clearly see that there are different grains of different kinds of rock that make that up. So there's different colors. It looks different to the naked eye. So it would be what we call a heterogeneous mixture versus a homogeneous mixture. So some definitions you should know here. Know the difference between a mixture and a pure substance, and know that mixtures can be broken down into homogeneous or heterogeneous, and know what those mean, and know that pure substances can be broken further down into elements or compounds. So one thing that can confuse people, or tends to confuse people a lot, is they'll ask me, what's the difference between a compound and a mixture? Because compounds are made of more than one element, so why aren't those mixtures? And the answer to that question is that a true mixture can be physically separated somehow into its different chemical components, and a compound cannot. So a mixture is a combination of two or more substances that you can separate into its different components. And a great example again is just salt water. We could boil off that water and you'd be left with the salt. And so you've physically separated the two components of the mixture. Whereas the compound water, which is H2O, so it's got hydrogen and oxygen, there's nothing that we can physically do to separate the hydrogen from the oxygen without doing some serious chemistry to that molecule. So we could use like electrodes and do a chemical reaction to separate those two elements, but that's not a physical separation. So the difference is a compound, in order to separate or purify a compound, you have to do some chemistry. A mixture can be physically separated into its different components. I wanted to start discussing this slide by saying that most of the rules that we're going to discuss in chemistry have some exceptions to these rules. And the rule about atoms being the smallest unit of matter that keep unique characteristics is one of those things that has exceptions to it. We'll talk about that more when we get into nuclear chemistry, because there are different types of atoms of the same element. So ignore all that, but keep it in mind in the back of your head that all of these rules have some exceptions to them. So when we talk about pure substances, that's matter that's made up of only one type of substance. That can be broken down into compounds and elements. Element is the simplest type of matter. It's made up of only one type of atom. So for example, elemental hydrogen is only made up of hydrogen atoms. We're going to talk later on about how do we determine what is a hydrogen atom versus some other atom or some other element like helium. We'll talk about what distinguishes between the two different types of atoms, or the many different types of atoms we have in our world. An atom is the smallest unit of matter that keeps its unique characteristics. So for example, all hydrogen atoms can combine with oxygen in a ratio of 2:1 to form water. So all hydrogen atoms can react with oxygen to make water. So they all will react in that way. A compound then is a pure substance that's made up of two or more elements that are chemically joined together. All molecules, we can call it individual pieces of compound molecules. So for example, in water, the molecule H2O is the individual unit with two hydrogen atoms and a single oxygen atom. That would be a molecule of water. So all molecules of water will act similarly to other molecules of water as well. So when you're first starting to study chemistry, the periodic table of the elements can be a little bit intimidating. So we're going to discuss that right now. All of the elements that we know exist are listed in the periodic table of the elements. And the periodic table of the elements is really a way to organize the elements to describe how they react with one another. So the periodic table of the elements is arranged in rows and columns. So the rows on the periodic table of the elements are called periods. I'm just going to refer to them as rows for the purpose of simplicity because this is a basic chemistry course. The columns are called groups. Sometimes I'll refer to those as groups. So we'll talk about like group 1A, group 1B, things along those lines. So when we say groups, I mean columns. I'm going to try to use one or the other, but sometimes I flip-flop in my head on that. The groups are numbered across the top of the periodic table from left to right. You're going to notice there's a 1A, a 2A, and then there's we'll get into that in a second. And then metals are going to be on the left of the periodic table of the element, and nonmetals are going to be on the right of the periodic table of the elements. Those two are going to be separated by this staircase-shaped line, which I'll show you when we get to the picture of the periodic table of the elements here in a second. So the periodic table has all of these blocks, and each block represents one of the elements of the periodic table of the elements. So inside those blocks, you're going to have a letter symbol. Sometimes you'll have the name of the element below the letter symbol as well, and there's going to be some different numbers in there as well, so we'll talk about what those numbers mean in a little bit. For many of the elements, the symbols are fairly simple, so they're derived from the name of the element. So for example, carbon is going to have the symbol C because that's just the first letter of carbon. Magnesium is going to be Mg, so it's two of the letters that are in magnesium. Some of these other ones are going to be a little confusing because you're going to be like, sodium, why is that Na? It's because it's derived from the Latin name. So sodium is natrium in Latin, and so it's Na. Gold is aurum in Latin, so it's Au. We'll talk about lead and lead poisoning because this is a medical course. So lead is Pb, and that's plumbum, because we used to use, or not we, but the Roman peoples used to use lead as their plumbing, and many of them would develop lead poisoning later in life. So we now know not to do that. So we don't use lead for our plumbing, but historically it was called plumbum because they used it for their plumbing. So that's why lead is Pb. All right, here's the periodic table of the elements in all of its glory. There are a lot of things going on in the periodic table of the elements. I'm just going to try to highlight things that I want you to notice. So, for example, we mentioned that we're separated by metals and nonmetals, and we kind of have this staircase looking thing going on here. And that separates our metals and nonmetals. So here you've got your metals, and here you've got your nonmetals. Now, like I said earlier, there's always exceptions to the rules. We've got one nonmetal, hydrogen's a gas, so he's hanging out over here. So that's one example of an exception to the rule. Some of the things that I also want you to learn about the periodic table of the elements for this chapter are going to be the positions of the alkali metals. So some of these alkali metals are going to be really important. So all of the group 1 elements the guys that are in this first column are going to be our alkali metals. Our group 2 elements are alkaline earth metals. Then we have the transition metals, which are these guys in the middle, which we're primarily going to ignore for the purposes of this course. There are going to be a few exceptions to that. We'll talk a little bit about like iron, which is in your blood. But for the most part, we're not going to talk much about the transition metal elements for this class. Then we're going to focus in on these guys over here. We've got our molecules that make up most of our organics. So we've got carbon, nitrogen, oxygen, phosphorus, and sulfur. These are all elements that are going to be highly utilized in biological molecules. We have our halogens. I want you to know that this whole group or column, 7A, are called the halogens. Halogens are very important. Some of them are highly toxic, but some of them are very essential for life. For example, chlorine, right here, Cl, sodium chloride, is one of the most important counterions for many of the salts in our bodies. It's an essential nutrient. Noble gases. These guys are called the noble gases because they don't really react with anybody. But I want you to know where they're at. They're important biologically because they can asphyxiate us. So they don't react with anything, but they also can displace oxygen. So I want you to know where the noble gases are. They're also used sometimes because they're a neutral gas and they don't react with anything, so we'll use them in chemical reactions as a neutral atmosphere. So we already mentioned that each block holds a different element, so we all know that. We know that the vertical columns are called groups, and the groups of elements have similar chemical behaviors. So all of those alkali metals, they're going to behave very similarly, and I'll show you a video when we get to class about how they react with water. All of our alkali earth metals are also going to react very similarly with water, and then all of our halogens are going to do similar chemistry with the human body, and all of our noble gases are going to do similar chemistry with different materials. So each group or each column has a letter and number designation. So the A designations are our main group elements. Those are 1 through 8, so it would be 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, and then our B designations are for the transition elements. So for the most part, you can ignore the B designations for the purposes of this course. So we mentioned our horizontal rows are called periods. Those can be numbered from 1 to 7. One thing I want you to know about the periods is that the periods describe how many shells of electrons an atom has, and we'll talk about that in greater detail in the future here. But as you go from left to right along the periodic table of the elements, we're going to start to see some different patterns when we talk about some of the other chemical properties of the elements. So when we talk about like electronegativity, which is the ability of an atom to hog an electron, we're going to see that that's going to increase as you go from left to right across the row or the period. So it's sometimes important to look at the columns on the periodic table, and sometimes it's important to look at the rows on the periodic table of the elements, so we look at both. So again, as we're moving from left to right, we're going to start out with our metals, and then we're going to transition into our non-metals, and that transition is going to happen along that staircase line there. And there's going to be a couple of different elements that border that little staircase line, and these guys are what we're going to call metalloids. They kind of act like a metal, and they kind of act like a non-metal. Again, if this was more of a general chemistry course, we'd go into that in greater detail, but this is more like a biologically based course. So an example of that is aluminum and like gallium. Some of these things are used in semiconductors and things along those lines. Not a whole lot of biologically relevant chemistry going on there with the metalloids, but it's interesting to know. So some of our elements are absolutely essential for human health. The elements that we need in the largest quantity are the elements that make up the majority of our biological molecules. So we're going to talk about carbon, hydrogen, oxygen, and nitrogen. I'm going to throw in there sulfur and phosphorus. Phosphorus is huge in our DNA, plays a huge role in our DNA. Sulfur in lower quantities is involved in some of our amino acids. So we'll talk about that in future chapters. Macronutrients would be other elemental things that we need in quantities greater than 100 milligrams per day. So this would be sodium, magnesium, potassium, calcium, and chlorine. These are things that we get through our diet. Of course, micronutrients we don't need in as high of quantities in our diet. So these things would include iodines. You might have like iodized salt, fluorine, which is of course good for your teeth. We put fluoride in our toothpaste, things along those lines. Iron, which is good for our blood. And there are several other elements that we need in very small quantities. So copper is actually one of them we use in very small quantities in our bloodstream. So here are some of our most common medically relevant or biologically relevant elements. So our most common elements in living things are going to be, of course, carbon. We're all carbon-based life forms. We have hydrogen, which kind of fills in the gaps in the bonds between carbon. We have nitrogen, which is involved in all of our amino acids and in our DNA. Oxygen, which is also involved in amino acids, DNA, and water, of course. And then we have our macronutrients, so sodium, magnesium, potassium, and calcium. These are all going to be ions that we use from anything from signaling in our neurons. So our neurons work based on electrical impulses. So they're going to use these positively charged ions to conduct an electrical current. They can be used to signal when a muscle cell should contract. Calcium's involved in muscle contraction, so essential for the heart and the rest of your skeletal muscles. We've got phosphorus over here, which makes up a huge part of the DNA backbone. Sulfur is involved in a lot of iron-binding proteins, so it's essential for metabolism in the mitochondria. So in the electron transport chain, sulfur is going to be involved, and that's how we produce energy. Chlorine is a common counterion for our important sodium, magnesium, calcium, potassium. And then we've got some other micronutrients that are cofactors for enzymes, so things that help our body bind on to other important things or do some chemistry. So we've got selenium, iodine, chlorine, we've got manganese, iron, copper, zinc, and molybdenum. So all of these things, you should start to familiarize yourself with these symbols. So if you see an H, you should know that's hydrogen. If you see a C, you should know that's carbon. So start to memorize these guys in particular from the periodic table of the elements. We've already discussed compounds a little bit, but I want to dive into compounds in a little more detail. So a compound, again, is a pure substance that contains two or more elements that are combined together with chemical bonds. We can have we're going to go into the different types of bonds in a later chapter. So we can have covalent bonds or ionic bonds. Salts use ionic bonds. But like I said, we're going to delve into that into a later chapter. The important thing to know from this chapter is that compounds combine the elements in specific ratios. So if you change that ratio, you no longer are talking about the same compound. So an example of that is water. Water is H2O. You have two hydrogen atoms to every one oxygen atom. If you have two hydrogen atoms and one oxygen atom, you are talking about H2O water. If you were to add an extra oxygen to that, so that you had, say, H2O2, you no longer have water. That's a completely different compound. It's going to have a completely different set of chemical reactions that it can undergo. So H2O2 would be hydrogen peroxide. So water you can drink. Hydrogen peroxide is very toxic. We use it to sterilize ourselves, so if you get a little cut, you can put that on, but you know that it burns. It is toxic to some degree. It will kill bacteria before it will damage our tissue at certain concentrations, so that's why we use it to sterilize wounds and things along those lines. Another example is table salt, sodium chloride. You're always going to have a ratio of 1 to 1. So you notice in the chemical formula that are shown here, we don't bother to show the 1 in subscript if there's only one of something. We just assume that because we've shown the symbol for the element there, that we know there's at least one of them. So in H2O, you don't say H2O1. For sodium chloride, we're going to assume that there's one of each of those because there's no subscript number shown. So the chemical formula is going to identify the type of element involved in the compound and the number of particles or atoms of each element involved in the compound. So it's going to tell you about the ratio. So the next thing we're going to talk about are mathematics in the sciences. So before we start to talk about how we do math in the sciences, we have to talk about what units we use to do math in the sciences. So we don't use the English system of units. We're used to using the English system of units in America here, where we talk about things in pounds, gallons, feet. And the problem with pounds, gallons, and feet is that as you're going from small quantities to large quantities of something, it's really hard to do the math, because as we break down pounds into ounces, it's like 16 pounds or 16 ounces per pound. And then when you get into gallons, it's even more complicated. It's just like 8 fluid ounces per cup, and then you've got 16 cups per gallon. It gets really confusing. So with the international system of units, everything's in multiples of 10. So let's introduce some of the units that we're going to use here. The standard unit for mass is the gram. So that's how much something weighs. We're going to do that in grams. And just to give you an idea of what a gram is, about a 1/4 teaspoon of sugar weighs a gram. So you can kind of picture that. If you multiply a gram by 1,000, we call that a kilogram. We're going to talk about the different prefixes that we can add to these base units. And a lot of people weigh themselves in kilograms in other countries. So we're used to a pound, and about 2.1 pounds is equal to a kilogram, just to give you an idea of the ratios there. So the standard unit for volume that we're going to use is the liter, and there are, I believe, it's like 3.5 to 3.7 liters per gallon, somewhere along those lines. It's in the 3 range, just to give you a ballpark idea of where that is. So that's our unit of volume, is the liter. We'll talk about milliliters is 1/1000th of a liter. So you need 1,000 milliliters to make up a liter. And in medicine, you'll often be asked to give someone a dose of something. If you're giving them an injection, that'll be in terms of milliliters. 1 milliliter takes up exactly 1 cubic centimeter of space. So you'll sometimes see volume in cc's, which is cubic centimeters. We're going to talk about that more in a little bit here, just to remind you of that fact. So 1 cc is equal to 1 milliliter, which is 1,000th of a liter, or a liter divided by 1,000. So the standard unit for length is the meter, and a meter is pretty close to the English yard, a single yard, or 3 feet. So these are the different prefixes that we can use if we're talking about really large quantities or really small quantities of those base units that we discussed. So essentially what you're doing is you're multiplying a particular number, or dividing a particular number, or the base unit by a particular number. So for example, if we have a kilogram of something, we have 1,000 grams of something. If you look at the line where it says kilo, the abbreviation we use is the lowercase k, and that means we're multiplying that base unit by 1,000. So if we have a kilogram, we have 1,000 grams. If we have a centigram, we are dividing a gram by 100. That means we have 1/100th of a gram. If we have a milligram of something, we are dividing a gram by 1,000. So if we have a milligram of something, we have 1/1000th of a gram. We could say that backwards and say that there are 1,000 milligrams in a gram. So I would like you to memorize all of these prefixes and the numbers involved with those prefixes. Most of them are in multiples of 10 to the 3rd power. They're multiples of 1,000. So for example, a kilogram is 1,000 grams. If you multiply a kilogram by 1,000, you have a megagram, 1,000,000 grams. If you multiply the megagram by 1,000, you have the gigagram. So you have 1,000,000,000 grams. And we go down the other way. If you go from gram and divide that by 1,000, you have the milligram. If you divide that by 1,000 again, you have the microgram, which is a millionth of a gram. And if you divide that by 1,000 again, you have the nanogram, which is a billionth of a gram. So just to give you some examples of things in these size ranges, we talked about the meter. The meter is about 3 feet long. So we all know what a millimeter looks like. You probably had a little ruler when you were a kid. But the thickness of your thumbnail or your fingernail, maybe close to a millimeter or half a millimeter. And if you get down to a micrometer is about the size of an E. coli cell. So a single bacterial cell is about 1 micrometer wide and 2 micrometers long. When you get down to nanometers, the width of DNA is approximately 3 nanometers wide. So the width of the ladder that makes up DNA, like a double-stranded DNA helix, is in the nanometer scale. The next thing we're going to talk about is equivalent units, and we're going to do a lot of examples of this in class because this is something that tends to throw people off. We're going to use equivalent units to create conversion factors that we can use to convert one unit into another unit. So one example would be getting from deciliters to liters. Our equivalent unit is 10 deciliters is equal to 1 liter. If you look at the definition of a deciliter is a liter divided by 10. So you would need 10 deciliters to be equal to 1 liter. So these two statements are interchangeable. We have the term 10 deciliters is interchangeable with the term 1 liter. So we can turn that into a conversion factor. A conversion factor, we can use the conversion factor to multiply the conversion factor against some other number and change the unit of that number. And the cool thing about conversion factors is all conversion factors are equal to 1. So you can multiply a number by any said number of conversion factors, and since all the conversion factors are equal to 1, you're not changing the value of that number. Why are all the conversion factors equal to 1? Let's take a look at that first one on the left there. It says 10 deciliters divided by 1 liter. Let's use the mathematical principle of substitution. 10 deciliters is the same as 1 liter, correct? So I could replace that 10 deciliters on the top of that fraction to say 1 liter. That's the same thing because we know 10 deciliters is equal to 1 liter. So if we have 1 liter divided by 1 liter, that's 1. So all conversion factors are some number divided by itself. All conversion factors are equal to 1. So you can multiply a conversion factor by a number. It will change the unit, but it will not change the value of the thing that you're multiplying it by. So a lot of our conversion factor problems are going to be word problems, and this is a step-by-step way that you can use to solve those word problems. So the first thing that we want to look at is we're going to determine what units are we trying to get to. Determine the units on your final answer. What are they asking you for? You're going to write that down somewhere. We're going to establish what information did they give us in the word problem. So anything that has a unit in, you're going to write that down over to the side of the word problem. If they tell you you're starting with 2 grams of this, and for every 2 grams of this is equal to 1 milliliter, you're going to write all those different pieces of information down on the side so you don't get confused. Then you're going to decide how to set the problem up. So what do we write down first? We're always going to write down the given unit first. The given unit is going to be the thing that only has 1 unit in it. Everything else is going to have, every other statement is going to have more than 1 unit in it, except for the answer statement. You're looking for this particular unit. And all those things with multiple units in it, those are going to be our conversion factors. So write down the thing with a single unit, and everything else is going to be a conversion factor that can get us to the final answer that we're looking for. And this will all become clear as we do examples in class. So we're going to do examples in class, so I'm not going to do examples of the conversion factor problems in these PowerPoints. It's just easier to do those on a board with you guys in person. So I'm going to move on to significant figures here. We're just going to briefly discuss what a significant figure is and why it's important. If you're trying to measure the weight of something, let's say, there are different scales that you could use. You could use a scale that's used to weigh a truck. You could use the scale that's in your bathroom, or you could use a really fine scale that's used to weigh a powder somewhere. All of those scales would give you a different number of what we call significant figures. For example, a scale that's used to weigh a truck might not even register my weight if I stand on it. So it's not accurate down to the pounds or even to the hundredths of a pound, or sorry, to 100 pounds. So we have to report, when we're reporting scientific information, we have to report it using the same number of significant figures that our equipment was able to accurately measure to. So you can't falsely report data that is more accurate than your equipment was actually able to measure to. So we're going to talk about how we do math without screwing up our significant figures based on the piece of equipment that we were using. So if someone gives you a measurement, typically all of the numbers in that measurement are significant figures. So we're going to show you some examples on the next slide of different numbers or different measurements, and we're going to talk about how we count how many significant figures are in that. Some of the things that can give us trouble are zeros, because you're not always sure whether a zero is significant or not. So let's say, for example, that a scale can only weigh to down to the 10 pounds range. It can't weigh individual pounds, but it can tell you if something weighs 10 versus 20 pounds. Then if you didn't know that about that scale, you wouldn't be able to tell whether or not the 0 at the end of the 10 was a significant figure or not. You wouldn't know, is this scale capable of weighing down to a single pound? I'm not sure. The number just says 10. It could have been exactly 10. It could have been 9 and the scale rounded it up to 10. I'm not sure. So that's where zeros tend to screw us up. So here are some great examples of that. A digit is significant if it is a non-zero number. So for example, if they tell you it's 41 grams, that means that that piece of equipment was able to accurately measure down to the ones column. So we know there's exactly 41 grams. If they tell you 15.3, you have 3 significant figures there. Zeros can screw you up. A 0 is significant if it is between non-zero digits. So if we say 101 pounds, we know this thing was able to or 101 liters, sorry. We know that this thing was able to accurately measure down to a single liter because they reported that 1 at the end of the number. So we know we have 3 significant figures there. Below we have 4 significant figures. If you have a 0 at the end of the number with a decimal point, the decimal point is an indicator telling you it is accurate to this level. So if they say 20 point grams, that means that we have a piece of equipment that is able to read to the ones column, not to the tenths column. So you couldn't go ahead and divide that by 3 and report anything beyond the ones column. If you had to mathematically manipulate this number, you would have to stop at the ones column. If we have a decimal point, again, like 9.800, we know that those zeros were added in there on purpose. Otherwise, they would have just stopped at 9.8. So we have 4 significant figures there. An example, if we go the whole way down to the bottom here, I want to show you an example where they have zeros at the end of a number, and those zeros are not significant. They're just placeholders, because we have 3,450,000 meters. So that's an example where we only have 3 significant figures, or we're unsure about the number of significant figures. We could have 3 significant figures, we could have 7 significant figures here. It depends on how accurate the piece of equipment that was measuring this is. So we'll do more significant figure problems in class, because I'm sure this is a little bit confusing until we sit down to work out problems using significant figures. So one of the reasons we need to pay attention to significant figures is that when we do addition, subtraction, multiplication, or division, we can create numbers that seem more accurate than they really are. So for example, if I weigh 1 gram of something and divide that by 1,000, I'm showing that I have 0.0001 grams of something now. So I'm not sure, if I report that, people might think that I had a machine that was able to measure that small amount of material, and I really don't. So sometimes when we manipulate measurements with math, we can give the false impression that we're increasing our accuracy or our certainty of a number, and that's not true. So we have some rules for significant figures in calculations. For addition and subtraction, our answers should be given to the least number of decimal places in the measured numbers. That means if we have more than one measured number, you count the number of decimal places in each number, and the number that has the fewest points beyond the decimal place, that's the number of significant figures that you use. And we'll give an example of that in a second. For multiplication and division, answers should be given to the least number of significant digits in the measured numbers. Again, we'll give an example of that in just a second. When we're doing our significant figures math, we're going to encounter rounding, so we're going to have to learn the rules for rounding. If the leftmost digit that's going to be removed when you're rounding is 4 or less, we round down. If it's 5 or greater, we round up. Scientific notation is a way to express numbers that are either very large or very small in a way that doesn't involve writing down a decimal place with a whole bunch of zeros and then a number, or a number followed by a whole bunch of zeros. So if you're talking about something that's extremely massive, so let's say that we're talking about a distance between two objects, and that distance is 2,800,000,000 miles away. We can say 2.8 times 10 to the 9th power. So we would use this general form for scientific notation, which is c. C is the coefficient. It's some number between 1 and 9, and n is the exponent that tells us the number of tens places that apply to that number. So, for example, if I have 10 to the 9th power, 1 times 10 to the 9th power would give me a billion of something. So if I'm talking in billions, I could multiply some constant c by 10 to the 9th power, and that tells you that I'm talking we have billionths of something. If I multiply that by 10 to the 6th power, we're talking we have millions of something, and 10 to the 3rd, we have thousands of something. We can also multiply by 10 to the negative something. So if I have 10 to the negative 3rd, I'm dividing by 1,000 now. And we'll do some examples of this in class as well. But 10 to the negative 3rd would be dividing by 1,000. So I would have a thousandth of something. And 10 to the negative 6th, I would be dividing by 1,000,000. So that would be a millionth of something. So we'll do plenty of examples of getting into and out of scientific notation in the problem-solving sessions in class. Here's a great example of what I was just discussing here. So if you have 1 times 10 to the 0 is 1. 10 to the 0 is the same as multiplying something by 1. If you have 1 times 10 to the 1st power, that's just 10. 10 to the 2nd power is 10 times 10, which gives you 100. 10 to the 3rd power is 10 times 10 times 10, which gives you 1,000. That's why I said if you multiply something by 10 to the 3rd, you're talking thousands of something. If you go the whole way up to 10 to the 6th, that's a million of something. So it's kind of good to get to know these numbers in scientific notation. I think the important ones are when you go up by factors of 3, because that's when you go up by 1,000, a million, a billion. That's usually where we put the little commas in when we're using numbers, so we're used to thinking in terms of thousands, millions, and billions. So if you go up by 10 to the 3rd, you're at 1,000. If you go up by 10 to the 6th, you're at a million. If you go up by 10 to the 9, you're at a billion. And we do the opposite. If we're going down, if we have a very small number like 0.001, we have 1 times 10 to the minus 3rd, which is 0.001. If we have 1 times 10 to the minus 6th, you have a millionth of something. So it's 0.000001. So we have a millionth of something, whereas 10 to the minus 3rd was a thousandth of something. I'm not going to spend a whole lot of time discussing percents because you guys should be pretty familiar with percents. You know, percent is when you have the part divided by the whole times 100. It's parts per 100. That's why we call it the percent. Cent is the Roman or Latin term for century, which is 100. So when you have parts per 100, that's why we say per cent per 100. So if you have the parts divided by the whole times 100, you have a percent. Or rather than working in percents, we can sometimes work in ratios, which is where we just don't multiply by the 100. So if you have 3 divided by 4, your ratio would be 0.75. That means you have 3/4 of something. If you multiply that by 100, it would be 75%. So we can sometimes speak in ratios. We can sometimes speak in percentages. Okay, we're out of the boring, complicated math stuff for a minute. We're just going to talk about some different chemical properties. So mass is one of the chemical properties that we're going to discuss. Mass is anything that takes up space and can be placed on a scale
and weighed. So it's a measure of the amount of material that we have in an object. We've already stated that the unit of measure that we're going to use for this is a gram. The weight of an object is determined by the pull of gravity on that object. So that can change depending on where you're at. As we get further and further away from the Earth, the weight of a particular material can change. So weight is not exactly the same thing as mass. Mass is the amount of the material that you have that can be weighed. So if you have, for example, 1 gram of water, it might weigh slightly more than a gram if you have it very close to the Earth than if you had it way out in the upper atmosphere. So weight and mass are not exactly the same thing. The mass is how many atoms do we have? That's how much of this material do we have that can be weighed. So there are some differences between weight and mass. For example, if you took the same mass of a human being, so me as a person, I weigh 215 pounds here on the planet Earth, but if I were to go to a heavier planet, I would have a higher weight because that planet would have more gravity, would be pulling down on me harder. So even though I have the same amount of mass or the same amount of matter, I would have a heavier weight on a different planet or a lighter weight on a smaller planet or body like the moon. Volume is the amount of three-dimensional space that something takes up. So we will often measure things, common things that we use to measure things at home are like measuring spoons or a measuring cup, whereas in the laboratory or in a medical setting, we're going to be using a graduated cylinder or a syringe to measure volume. The typical unit that we use in the lab is the milliliter, and in medicine we're going to use the milliliter because those are typically units that we'll be using to inject into people or to measure small volumes of things. We'll often use the liter too, especially to express concentration. We'll say grams per liter or something along those lines. If you're talking about concentration, how much drug do we have in this particular solution that we're going to be injecting into this person. But oftentimes we'll speak in milliliters. I mentioned earlier that a milliliter takes up exactly 1 cubic centimeter or a cc of space. So there are 3 units that mean exactly the same thing. And this can be a little bit confusing to people, but I want you to get this straight in your head. 1 milliliter is equal to 1 cc is equal to 1 centimeter cubed. Cc just means cubic centimeter. Centimeter cubed is a cubic centimeter. And a milliliter takes up the same amount of volume as a cubic centimeter. So if a doctor asks you for 5 cc's of something and your syringe only has mLs, he wants 5 mLs. It's the same thing. So if I give you a problem, a math problem to do in class, and I give you everything in mLs, but then ask you for how many cc's do we need, you should be able to figure out, well, a cc is the same thing as an ml. So I can just give him the answer in mLs, or I can just change the ml to cc in my final answer. So don't get tricked by that little trip up there. 1 ml is the same as a cc is the same as a cubic centimeter. Density is the next important chemical property that we're going to discuss. Density is used to determine whether something's going to sink or float. It's the ratio of a substance's mass to its volume. So something that has a high density would have a lot of matter packed into a small amount of space. So examples of that are some of our really heavy metals. An example of that is shown here versus wood, which is basically a hydrocarbon material. And as you can see here, these materials have different densities relative to water. The density of water is 1 gram per milliliter. If you have 1 gram of water, that takes up 1 milliliter of space. That's one of the reasons that they set the units of grams and milliliters. They used water to determine those units or to come up with those units. So if you have 1 cubic centimeter of water, it weighs a gram. It's going to have 1 gram of mass. So water has a density of 1 gram per milliliter. If something sinks in water, you should be able to tell me that its density is greater than 1 gram per milliliter. If it floats in water, its density is less than 1 gram per milliliter. So if I told you that an oil had a density of 0.7 grams per milliliter and asked you, will that sink or float on water? You should tell me it will float. And if I ask you why, you shouldn't write down because it's an oil and I know oils float. You should write down because its density is less than the density of water. Sometimes when you're reading material safety data sheets or other documentation that comes along with a particular material that you might encounter in the workspace, instead of density, it might give you specific gravity. I'm going to tell you specific gravity and density are pretty much the same thing, but specific gravity doesn't have any units because we're dividing the density of the sample by the density of the water. And the units of both the density of the sample and the density of water are grams per milliliter. So if you divide one thing by itself, it becomes 1. So the units disappear. So specific gravity is just the ratio of the density of the thing that you're talking about versus the density of water. And the density of water is 1 gram per milliliter. So you're not changing the number. You're just talking about the ratio. So if the specific gravity is greater than 1, then that material is going to sink in water. If the specific gravity is less than 1, that material is going to float. This can be important medically, especially if you're making up a solution that you might inject into somebody and you're mixing things with different specific gravities. If you tend to mix them and then let that solution sit for some amount of time, the two might separate. So you might have to mix the stuff before you go to inject it into somebody because it might separate on standing. So this can be an important thing in the medical field as well. So we have many different units for temperature that we use here in the United States. Typically we use Fahrenheit, but the rest of the world uses the Celsius scale. And scientists are going to use the Celsius scale. In the field of medicine, sometimes they'll use both. Oftentimes when we're talking about a person's internal body temperature, we're going to use the Fahrenheit scale because it's easier to talk to a patient in terms of the standard of, or the system of units that they are used to discussing. So if you told a patient that their body temperature was 37 degrees Celsius, they would freak out because they would think that they're freezing to death or something along those lines. You know, we're supposed to have a body temperature around 98 degrees Fahrenheit. So the two scales are very different. We're going to do very little math for the conversions because everybody has cell phones nowadays. If you need to get between Fahrenheit and Celsius, you whip out your cell phone and get to a conversion factor program. Just Google it. So I'm not going to make you memorize this Fahrenheit to Celsius conversion for this class or anything along those lines. But I do want you to know some basic points like what's the freezing point of water in Fahrenheit, what's the freezing point of water in Celsius, and the boiling point of water, so you can relate between the different scales. A third scale that scientists use is called Kelvin. And we work in the Kelvin scale because the Kelvin scale contains this absolute value 0. So we sometimes call it the absolute scale. You know that in the Fahrenheit scale and the Celsius scale, we can have numbers that have negative values. In the Kelvin scale, we don't have any negative values because the coldest anything can get on this planet is negative 273 degrees Celsius. The Kelvin scale starts at negative 273 Celsius. So to convert something to Kelvin, we take Celsius plus 273 degrees. So 0 Kelvin is as cold as any material can get. It does not get any colder than that. We call that absolute 0. So to use Kelvin, that takes away the trouble of negative numbers when we're trying to do math, when we're talking about like how gases expand and things along those lines. Having negative numbers in our equations really screws us up as chemists. So we'll sometimes talk in Kelvin. And when we get to working with Kelvin, we'll do some example problems of converting from Celsius to Kelvin. So let's take a look at some of the differences on the scales. If we take a look at the freezing point of water, the freezing point of water in Fahrenheit is 32 degrees Fahrenheit. The freezing point in Celsius is 0 degrees Celsius. And in Kelvin, that is 273 Kelvin. Remember, 0 Kelvin is absolute 0. That's as cold as anything can get. If we go to the boiling point of water, that's at 212 degrees Fahrenheit, and Celsius is 100 degrees. So you can see that water was used as a standard to create the Celsius scale. So pure water boils at 100 degrees Celsius and freezes at 0 degrees Celsius. The body temperature, typical body temperature, is about 98.6 degrees Fahrenheit. That's about 37 degrees Celsius. These are the conversion factors that we use to get from the different units of temperature from one to another. As I said, we are not going to use these in class, or you won't have to memorize these for class. We're going to use our calculators, or we're going to pop out our cell phones and just be able to convert from one to the other there. So some important temperature numbers to know, especially in the medical field, is normal body temperature. That's 98.6 degrees Fahrenheit or 37 degrees Celsius. If that body temperature begins to rise, for example, if we have an infection, or it can also rise because you are out on a very hot day and your body is not cooling, so our body temperature can rise in those conditions, especially if you become dehydrated and you can't cool yourself off. You can reach a hyperthermic state, which means that you are too warm. This condition causes convulsions, coma, and can result in permanent brain damage and even death. So that can occur above 40 degrees Celsius or 104 degrees Fahrenheit. This is one of the reasons why it is very important to try to get people into the hospital if their temperature rises above, say, 103 degrees. We're approaching that danger zone where we're going to need to get to a doctor now and see what we can do to lower that temperature, get some ice packs on that person, or do something along those lines to get that temperature down. On the opposite range, if you drop to 35 degrees Celsius or 95 degrees Fahrenheit, you can reach a hypothermic state. At that point, your body's chemical reactions actually slow down to the point where you're going to feel cold, have an irregular heartbeat, and slow breathing rate. And if you drop much below that, that can result in serious problems and even death. So the next thing we're going to talk about is energy and what units we use to discuss energy. Chemists often will use the joule, but we tend to use the term calorie as Americans, and most of the average common people typically are used to hearing the term calorie for energy. When we think of calorie, when I say calorie as a chemist, I don't mean the same calories as what's on the side of your cereal box. So for the terms of our chemistry class, if I use the term calorie with a lowercase c, I'm talking about 1 calorie as it is equal to 4.184 joules. The calorie on the side of your cereal box is actually a kilocalorie. It's actually 1,000 calories. And we should say kilocalorie on the side of your cereal box, but instead they use capital C calorie. I didn't come up with this system. It's confusing, but it's just something you're going to have to memorize here. So nutritional calorie is 1,000 times a single chemical calorie. So another really cool chemical property is heat and specific heat. So what is heat? Heat is the kinetic energy that flows from a warmer body to a colder one. So if something has been heated up, its molecules or atoms that make it up are actually moving faster. So they're actually vibrating, and that is where the energy comes from. It's actually a kinetic energy. Heat is a kinetic type of movement energy. And so if you touch a hot pan, it actually speeds up the molecules in your hand to the point where it causes like a burn. It's increased friction, it's increased movement and speed. This is one of the reasons why you can give yourself a burn by just rubbing your finger back and forth really fast on carpet. So you can give yourself a friction burn. It does generate heat. It's kinetic energy. So all substances have the ability to absorb or lose heat, and they can do that at different rates depending on their chemical properties. So some substances have they will absorb heat very quickly. They have a different specific heat. So we're going to discuss specific heat now. The specific heat as a substance is the amount of heat that's needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. So things that have a very low specific heat will heat up very quickly. So things like metals will have a very low specific heat. It does not require a whole lot of heat energy to raise the temperature of them. So things like water require a vast amount of energy to change the temperature. This is why it takes water so long to boil. If you take a pot and put it on your burner without any water in it, the metal will get very hot very quickly. Now, if you add water to that, water requires a lot of heat to get it to heat up. This is due to the very strong interactions between water molecules. If you take a drop of water and put it on a table, those water molecules bind to each other with such strength that they actually fight gravity. That's why water will beat up. So there's a very high amount of energy in those chemical bonds between those water molecules. So it requires a lot of heat to break those chemical bonds to get water to start moving, to get it to start having heat. It takes a lot of energy to do that. So that's one of the reasons it takes water so long to boil when you put it on a burner versus the metal heats up almost instantaneously. And this is one of the reasons why we use water to fight fires. Water absorbs a ton of energy off of that fire. You can drop a small amount of water onto a fire versus if you're trying to cool off water with some other substance, if you're trying to cool off a fire with some other substance, you'd need a vastly larger amount of that substance. So water is a substance that we have a ton of on this planet, thankfully, and it absorbs a lot of heat. So that's one of the reasons why we use it for firefighting. So here are some examples of specific heat. We can see that some of the things that we use for like insulation have relatively high specific heats compared to other materials. So we could use, for example, brick would insulate your house fairly well compared to if you had a copper roof or a stainless steel roof or something along those lines, or stainless steel walls or copper walls. We wouldn't want to use those for insulation. So water is also very insulating. So our bodies are made up of like 70% water, and they insulate the heat in our bodies very well. This is why it takes us a fairly long amount of time to like freeze to death or to become overheated if we're exposed to extreme weather conditions. So the next property we want to discuss are the states of matter. So whether something exists in a solid state, a liquid state, or a gaseous state. So if something exists in a solid state, the particles, molecules, the atoms that make up this material are very tightly packed together, and they are barely moving. So they might be vibrating a little bit, but they're not really exchanging partners. The molecules are rigid, stuck, kind of trapped in the same spot. They're not going to be jumping around or moving a whole lot. And this is what makes solids so rigid and what makes them maintain their shape. Like they won't conform to the shape of a container that they're put in. You could put if you had a 6-sided dice, you could put that into a large shipping box, and it's not going to expand to fill the container up. A liquid is going to take on the shape of its container, but not totally expand out to fill up the volume of that container, unless you continue to pour more and more liquid in. So in liquids, the particles are less ordered than they are in solids. They are able to change partners, so they're going to interact with one another. They're going to have some attractive forces that are holding them together, but those forces aren't holding them still in space. They're able to move and go from one spot to another throughout the beaker in this particular example. So this is one of the reasons why liquids are fluid. If you dump a liquid, that liquid can spread out. It can spread out to fill the container that you put it in. But the molecules are still held together, so they're not going to expand to fill the container. So in a gas, there is nothing holding the molecules together anymore. So the molecules or particles or elements or whatever that makes up that gas, they are no longer held together. They have enough energy that they are not interacting with one another, and they're going to bounce around and fly through the room. So this will expand. Gases will expand to equally fill up all parts of their containers. So a perfect example is a balloon. If you put a little bit of gas in where you blow it in the mouth hole, it'll expand and fill up the entire container of that balloon. So again, just to highlight some of those differences, solids have a definite shape and volume. That shape and volume can change if you manipulate the solid, but if it's just sitting there, the shape and volume will not change. Liquids have a defined volume, but can change their shape. So the liquid will change its shape to conform with its container. Gases do not have a defined shape or volume. Gases can change their volume to expand to fill the entire container in which they are placed. Well, this table just summarizes the different properties of solids, liquids, and gases. And you can review this in your book. To wrap up our discussion on properties, we're going to talk about a few other definitions on measurements. So if we're taking measurements of chemical properties, we need to determine whether or not we're being accurate versus precise. So let's talk about accuracy and precision. If your measurement is accurate, that means it is close to the actual or true value. Precise measurements are similar in value, but they might not be close to the actual value. So let's say you're trying to measure the same thing, and that thing weighs 3 pounds. An accurate measure would be, if you measured it a whole bunch of times, the average came out to equal about 3 pounds. A precise measure would be if you got 3 pounds on the dot every time, or you got the same result on the dot every time. Something can be precise but not accurate. Let's say we were weighing something that was supposed to weigh 3 pounds, and the scale told us 6 pounds every time. The scale was precise, it told us the same thing every time, but it was off, so that wasn't accurate. So that's the difference between accuracy and precision. One of the problems that we can bump into in the medical field is that we try to be scientists, and so we use the standard international unit of measurement, and people in America are used to using the U.S. customary unit, so we kind of have to be able to, at least a little bit in our head, go back and forth between the two a little bit. So some common conversion factors to be aware of out there, there's about 2.2 pounds per kilogram. So a lot of times drugs will be dosed in milligrams of drug per kilograms of body weight. So you might have to get back and forth between kilograms and pounds. So you want to know that 2.2 pounds per kilogram number is a good one to have in your head. 1 quart is approximately equal to 1 liter, so 1.06 quarts. That's why about 3.7 liters per gallon was a number I threw out there earlier. Fluid ounces, 1 fluid ounce is pretty close to 30 mLs. So if a drug is dosed in a 30 mLs, you can tell somebody to give a fluid ounce of that particular compound. Teaspoon is roughly equal to 5 milliliters, so a teaspoon of water, a teaspoon of a drug dissolved in water would be about 5 mLs. So if somebody doesn't have a little syringe to give their kid medicine out of that has mLs marked on it, you could tell them roughly how many teaspoons to give the child. And then there's units of length don't come in as often in the medical field. So if you're in the medical field, one of the things that's going to happen is you're going to have to learn how to read laboratory reports. So if you send something in for a test, you could get a report back. And these are things that, I'm not going to throw this out on the test here, but these are things that we'll discuss in class when we get into the problem solving sessions a little bit. So a lot of times when you get a lab report, you're going to be given results that are given along with normal limits for a particular compound. So if they're taking, for example, levels of calcium ion in the blood, they'll give you a number along with what is normal for that number. If the result is out of range, they will have that highlighted. Sometimes they'll give you the values relative to something, so they might be equal or less than 1, and so they have a different set of rules, and you'll learn more about that in your nursing classes. Most of the units that you're going to come into contact with, because these are measurements that are in the lab, we have scientists running these tests, so the units are going to be in metric. So if you want to describe this to the patient, you might have to be able to do a little metric to standard American units math in your head. Another unit that you might see fairly often, especially when they're talking about small quantities of something in the blood, might be a millimole. A mole is something that we use to count the number of particles in chemistry. So we're going to get to, in a later chapter, what a mole is, and a millimole would be 1,000th of a mole. So a mole divided by 1,000. We'll talk about what that means when we talk about the mole. And again, in the United States, we often use body weight measured in pounds, but a lot of pharmaceuticals are dispensed by body weight in kilograms. So that 2.2 2.2 pounds per kilogram conversion is going to be a good one to keep in your head. One of the things that we're going to do in the problem-solving sessions, a lot of, is going to be calculating a dosage. This is going to be just a basic conversion factor problem. So we're going to determine what are the units that we want in the final answer. For example, they might say, how many cc's of this drug should we give to someone? So then we're going to take and read the whole word problem, determine out the information that was given to us. They might tell us, for example, that you're supposed to give 0.2 cc's for every 10 kilograms the patient weighs, or something along those lines. And the patient weighs 52 kilograms. So then you're going to have to write all of that information down. So we'll determine the given information and write it down on the side of the problem. And then we're going to determine what is a conversion factor here. And the conversion factor is going to be something that has more than one unit in it. And then we're going to determine how do we set up this equation. So we're always going to start with a piece of information that only has one unit in it. We're going to multiply that by a conversion factor so that the units cancel except for the unit that we're looking for in the final answer. And we'll show you how to set these up when we do these problems in our problem-solving sessions in class. When we're talking about dosing, oftentimes in a hospital setting, we're also going to have to take into consideration that these drugs are going to be given by IV. And sometimes we'll want these drugs to be given over an extended period of time. You wouldn't want to give a drug too fast if the body could have a negative reaction to that. So oftentimes we'll have to use what's called a drop unit or a drop factor. So the IV delivery of medications is measured in drops per milliliter. So that's abbreviated GTT per ml. And we can use a drop factor to determine the drip rate, or what drip rate is necessary when we want to give a prescribed volume of medicine over a given time period. So that can change depending on the diameter of IV tubing that we have in. Smaller diameter IV tubing might give smaller volumes of drops, so you'll have a different drop factor there. And we'll try to do a couple of problems along those lines when we do our conversion factor problem solving in our in-class sessions. We talked about percents earlier, but while we're talking about dosing, I want to mention that you can use the term percent to mean slightly different things. So, especially when you're talking about drugs, a pill might say, what is the percent active ingredient of this pill? So that's different from different types of percents. So the percent active ingredient is the percent of the mass of that pill that is actually the drug. Because often we'll use other binders and things that increase the size of a pill, and those are typically put into the pill, number one, to make it something that you can physically hold, because if it's a very tiny dose of drug, pills would be really tiny, they'd be hard to handle. But if it's a large amount of drug, sometimes those binders are necessary to cause a slow release of the drug. So if you want the drug to last the entire day, that binder will slowly dissolve in your digestive system and be released throughout the body slowly over the course of a day. So there might be a small percent active ingredient compared to the whole size of the pill. We could also use the term percent of an adult dose. So because children are often administered a smaller amount of a drug, we might have a particular percent of adult dose that's prescribed for a child of a certain age or a child of a certain weight. We could also have percent in nutrition labeling. This would be how much, like a percent daily value. Did you get the proper percent of this particular vitamin in your diet that you should have in this particular day? Finally, we're going to move on to section 1.6, and we're going to talk about changes in matter. So we're just very briefly going to talk about physical changes and chemical equations and how we balance them. We're going to do more balancing examples in class, so there's going to be very little balancing examples here in this particular PowerPoint lecture, but we'll do many more examples in our problem-solving sections in class. So a physical change is a change in the state of matter. So if you're going from liquid to solid, that would be freezing, and that is a physical change. A chemical change is different from a chemical change, or different from a physical change. In a physical change, you had, in the example previously, you had the liquid form of water was turning into the solid form of water. The substance didn't change. It was still chemically water. But in a chemical change, we are taking one or more substances and rearranging how the atoms are strung together and making new materials. So in a chemical change, you do not end up with the same material. In a physical change, we could go from solid to liquid to gas, and it's all the same material. That in our example earlier, it was water. For a chemical change, the substance is actually undergoing a chemical reaction and is no longer going to be the same substance when it is done. A chemical equation is a way that we write out what happened in the chemical reaction. So we've got an example down there in the bottom right of the slide. We have carbon. This might be like carbon in the form of graphite or carbon in the form of coal reacting with oxygen. So we're burning something. We're producing heat. So we've got on the left side, we have our reactants. These are the things that we start with. The reactants are the starting material. They're going to do the reacting. And the final product in the end is on the product side of the equation. So we have the left side of the equation, the reactants. The right side of the equation is the products. And then we show an arrow. And the arrow points in the direction that the reaction is moving. We'll talk a little bit, especially in biochemistry, you can have a multi-directional arrow. So we can have sometimes the body will break down a material and turn it into a product, and then it can take that product and break it back down into the reactants if it needs the reactants again. So sometimes that arrow goes both ways. For many reactions, though, we'll just have an arrow in a single direction, and that means this reaction just goes in this direction. It's very difficult to turn CO2 back into carbon and oxygen. Plants can do it with the help of sunlight and some enzymes and things along those lines, but chemically it requires a lot of energy, which plants get in the form of sunlight. So we have our reactants, our reaction arrow, and our product. Sometimes we'll also show in our chemical equation, we're going to show the symbols for sure of the different elements involved or the different compounds involved. So we have our C for carbon, our O2 shows that we have oxygen gas. O2 is the chemical formula for oxygen. The gaseous oxygen that we breathe in is O2 in our atmosphere. And that produces CO2 or carbon dioxide. So we have all the different chemical formula of the individual compounds involved here. You'll notice there's also in parentheses, there's a little S. That can stand for the state. So we have solid. In parentheses, we have gas. We could also have a liquid. Perhaps something reacts and can make liquid water. In this case, we have solid carbon reacts with gaseous oxygen to produce gaseous CO2. The law of conservation of mass means that matter can neither be created nor destroyed. So if we start out in the previous example where we had carbon reacting with oxygen to make CO2, our chemical equation will also conform with the law of conservation of mass. We're going to keep track of every atom of carbon and every atom of oxygen in that particular equation and make sure that the equation is balanced. We don't want to accidentally create carbon or accidentally create oxygen. It just so happens that the previous reaction that we're looking at is balanced. We have one carbon atom reacts with two oxygen atoms to make a new molecule, CO2. So we have the same number of oxygen atoms on the left and right of the arrow. We have the same number of carbon atoms on the left and right of that arrow. But that doesn't always happen. So sometimes we're going to have to balance the chemical equation. We do this by adding coefficients, which are numbers in the front of the chemical formula. So the coefficient is going to go in front of the chemical formula of the compound. We're never going to change those little numbers that are in the subtype. So for example, if we had carbon reacting with 3 oxygens, O3 somehow, we wouldn't just write CO3. We'd have to balance it by adding coefficients. If we change the subscript number, we're changing the compound. So we can't do that. We know that carbon reacts with oxygen to make CO2. It always makes CO2. So we can't change that subscript number to balance things. We have to add numbers out front. When we add a number out front of the chemical or the compound formula, that means that we have more than one of this compound or more than one of this atom, involved in the chemical equation. So we're going to do plenty of examples of balancing chemical equations together, but I just want to go over the different steps involved. It's actually quite simple here. So the first thing that we want to determine is it balanced? So do we have the same number of each atom on the left side and the right side? So you're just going to count all the carbons, all the oxygens, all the whatever element are involved. Do I have the same number on the left as I have on the right? If so, it's balanced. You're done. If not, we have to proceed to step 2. So to balance the equation, we're going to add coefficients to make the numbers equal on both sides. So let's say we have 1 carbon on the left and 2 carbons on the right. We could add a 2 to the carbon on the left, and that's going to change we're going to add that coefficient there. That's going to change the number of carbons we have on the left. So we're going to do that to balance. We're going to add these coefficients. We want to start by balancing elements that only appear once on a given side. Sometimes if you have multiple compounds in the equation, you might have oxygen or carbon or some element in more than one compound on the same side of the arrow or on the same side of the equation. So you want to start, it'll make things simpler for you if you start by balancing elements that only appear on one compound on a given side. Finally, we're going to just repeat those first steps. We're going to see now that we've added a coefficient. Is the equation balanced? If not, we're going to continue to add coefficients until we get that puppy balanced. That concludes our lecture on Chapter 1. So congrats on getting through that massive PowerPoint presentation. We have a Chapter 1 study guide. You can flip through those slides at your leisure. And also, you can email me with any questions that you have, and we will do a lot of example problems in our in-class learning sessions. Thank you.